All right, now that we have discussed some of the basics of generalized linear modeling of log normal, Poisson, and binomial data, there's one additional concept that we really need to understand in order to fully implement what we've learned, and this is called overdispersion. Now, overdispersion is a bit of a complicated topic, but it is important for you guys to know before you start using GLMs, otherwise I wouldn't be forcing you to do it. Overdispersion stems from the fact that Poisson and binomial GLMs have a very specific mean variance relationship. Right? This is because, unlike a normal distribution, a Gaussian distribution, where you've got a mean and a standard deviation that defines the shape of the distribution, you've got two parameters. For a Poisson and binomial distributions, you only have one parameter. Right? The mean and the variance are actually locked together in that single parameter. And so when you're working with these types of data, this is part of the reason that we kind of expect some heteroscedasticity in our models, as we talked about before. And so when we're building Poisson and binomial GLMs, we often encounter this issue of overdispersion. And this occurs when our mean variance relationship in the data kind of extends beyond what we are able to permit given the parameter of our kind of distribution. You can have overdispersion, you can have underdispersion, but in both cases, it's a violation of this mean variance relationship. To make some sense of this, let's actually pull up some data. So let's pull up our ArcData package and load in data from the Nelson data set. This is a data set of pottery types and their counts at an archaeological site in New Mexico across 10 different depths, stratigraphic units. So let's plot what we're dealing with here. Let's plot type 1 ceramic counts. That's just a kind of one-color glazed ceramic, I believe, and plot that as a function of depth. Now, when we plot this, we can see that as depth increases, as we go deeper in the site, the counts of type 1 ceramics increase. It goes from kind of 0 towards the top of the site, and as we go deeper, we're up towards like 120 into the kind of 100 and 120 range. And so we know how to build a GLM from this, right? If we wanted to make a GLM, we would have an object, and we would say, all right, give me the type 1 pottery counts as a function of depth at the site. Data equals Nelson, and in this case we want family equals Poisson. And this is because we're dealing with count data, so we want a Poisson model. Now notice that I didn't specify Poisson, open parentheses, link equals log. That's actually implied when you just say Poisson, so you don't always need to say that if you don't want to, but generally for official purposes I would recommend saying family equals Poisson, link equals log in parentheses. And so this GLM here, if we inspect the summary of it, as we've done so many times before, and scroll down a bit, we'll see that there's a value here in the middle of the output, dispersion parameter. And it says the dispersion parameter for Poisson family taken to be 1. What this is referring to is this idea of a mean variance relationship, that the relationship between our mean and variance is taken to be 1. More technically speaking, the relationship between our residual deviance and residual degrees of freedom is taken to be 1. Again, this is all very technical, but what we just need to know is the fact that there is the possibility that our data are over-dispersed. And when we look at this, it does look like the data, if we were to fit a model to this, I suspect the model would be really tight through these values of kind of 0 to 6. But then as soon as we start getting up towards 7, that confidence interval is going to spread out a lot. There's going to be a lot more uncertainty in our model. I suspect that means that we've got pretty strong heteroscedasticity, which is a problem for Gaussian linear models, but is kind of assumed for Poisson models. But it's only assumed up to a point. And so to make sure that we're not suffering from overdispersion, what we can do is a couple different things. There's some statistics that you can find online that you can run to check out what's going on here. But what I simply like to do is apply the solution to this problem and then see what the summary output tells us. And the solution to this problem is to use what's known as a quasi-Poisson distribution. And so in general, a quasi-family GLM or a quasi-family distribution is kind of an extension of a Poisson or a binomial distribution, where you kind of correct it a little bit whenever that mean variance relationship isn't quite right. And so if we were to take this GLM code that we've got here to define the GLM, and we simply add quasi to the front of the Poisson argument there, if we run this, we've now built a quasi-Poisson GLM instead of just a Poisson family GLM. If we inspect the summary output for this now and take a look at what the dispersion parameter says, dispersion parameter for quasi-Poisson family taken to be 16.7. Right? I said before, if we looked at the output from the first version of the model, it was taken to be 1. The model was assuming that it was 1 because that's what a Poisson distribution would specify, that this relationship between the deviance and the degrees of freedom is 1. In actuality, now that I've fit a quasi-Poisson distribution, it's telling us what the real dispersion parameter is, and the real dispersion parameter is 16.71. That is not a value of 1, right? Generally speaking, acceptable ranges for the dispersion parameter range from 0.9 to 1.1. There's a little bit of wiggle room around that. Again, this isn't a hard cutoff. This is just kind of a ballpark estimate for when overdispersion could be problematic if you're higher than 1.1, or when underdispersion could be problematic if you're less than 0.9. If you're at like 0.85 or 1.15, it's probably not the worst thing in the world, right? But a value of 16 like we've got, that's huge. We're definitely overdispersed. And the meaning of this, whenever you have overdispersion, it messes up your p-values, right? It leads to incorrect p-value calculations. Whenever your model is overdispersed, you're more likely to find a false positive. You're more likely to have a significant p-value when you shouldn't have. Whenever your model is underdispersed, you're actually more likely to kind of miss out on a false positive, perhaps have a false negative, miss out on finding something that's real. So underdispersion is less of a problem because it's more conservative, but overdispersion can lead you to find significant things when there really shouldn't be, or there really aren't significant things to find. And so we really need to correct for this. And the way that we correct for this is what I already did. I said family equals quasi-Poisson instead of family equals Poisson. This model output that I've got now is corrected. It's a quasi-Poisson model. And there's some complications with this that make it a little bit trickier if you're getting into some higher level modeling stuff. But for most purposes, this is a perfectly acceptable thing for you guys to do. Another thing I do want to note is when you're calculating p-values with quasi-family distributions, things are a little bit trickier. Right? If we want to use that library LM test and pull out the LR test function from there, as we've done before, look at the output from our GLM object when we feed it into the LR test function. There isn't a p-value, right? It doesn't actually report anything because it can't actually calculate a p-value with this function. This function is only meant to be used with non-quasi-family distributions. It's only meant to be used for Poisson or binomial or log normal models, not quasi-binomial or quasi-Poisson. LR test won't work for that, unfortunately. And so what we actually need to do is use a function that we've already seen before, the ANOVA function. If we feed the ANOVA function our GLM object, and we specify test equals f, what it does is actually run a likelihood ratio test for us. This is a likelihood ratio test, specifically an analysis of deviance instead of an analysis of variance, since we fed it a generalized linear model where we have deviance is what matters. And so this ANOVA function here is actually running a likelihood ratio test, just like the LR test function is. But the LR test function, as I said, is only meant to work for Poisson and binomial and log normal and some other basic non-quasi-family distributions. And it does that because it runs a chi-square test. This is a bit in the weeds, but the reason that it won't work is because whenever you switch to a quasi-Poisson model like we just did, you can no longer really know the deviance exactly. You're switching over to estimating it. And so when you estimate it, you actually need to use what's called an F distribution, which we have seen before. Many times, actually. But so when we run this ANOVA function here, this is using an F statistic. So we would report this as F equals 21.93 degrees of freedom equals 1, and the p-value is less than 0.01. Right? So this is kind of the accommodation that you need to make when you use quasi-family distributions. If you were just making a Poisson model, you could use the LR test function as normal. That would be perfectly acceptable, and use that chi-square statistic that it's going to give you, because a chi-square distribution is for known variances, or in our case deviances, whereas an F distribution is for estimated variances or deviances. Again, that's pretty in the weeds for the level of this course, but it is an important thing that you need to know, that when you're following this kind of workflow for a quasi-Poisson model, you've got to use the F-test version of this ANOVA function, and that's going to give you your likelihood ratio test p-value that we really care about. Now, there's also the possibility that we could have underdispersion, as I said, right? Let's test that out. I want to create an index value, because there's a way that we can do this with a binomial distribution as well, because just like Poisson distributions, you can have a quasi-binomial distribution. And so with the Nelson data, let's take the type 1 pottery counts, and let's run a little bit of a calculation here. Let's take type 1 pottery counts divided by the sum of type 1 and type 2 red counts. So there's different, if we inspect that Nelson object, right, we've got type 1 pottery, we've got type 2 red pottery, and what I've done here is create an index, a new column of the Nelson data frame. And I said, all right, using this with function is kind of a cool trick, with the Nelson data frame, take the type 1 count and divide that by the sum of the type 1 and the type 2 red pottery counts. If I do this and then inspect what we've got proportions ranging from 0 to 1, telling me out of the total number of type 1 and type 2 types of pottery, what proportion of those are just type 1. That's what this index value is telling us. If we plot the index value through the depths of the site, we can see the relationship that we're looking at here is also an increasing one, where we've got a little bit more variation in here, but it increases pretty strongly and pretty kind of pretty much in a tight pattern, right? Which is really perhaps going to cause a problem for us in this case if it's a little too tight. And so again, always be on the lookout for over-dispersion or under-dispersion when you're doing these generalized linear models. And so if we make our second NelsMod, which is called NelsMod 2, of the index as a function of depth using the Nelson data, and in this case, because it's a proportion, the family is binomial. Same deal as before. If we just say equals binomial, we don't need to actually specify link equals logit, because that's implied. And so we make this model, and we actually get a warning. In eval family, non-integer successes in a binomial GLM. This is fine. It's a warning message, which means that our code still ran. It wasn't an error. It was just a warning. And it's warning us because technically a binomial family distribution is discrete, where it only takes zeros and ones, but we fed it data that are actually continuous and simply bounded by 0 and 1. And that's why it gave us this warning. Don't worry about it. It's not a big problem. It's not really a problem at all. It'll still work, and you'll still have a legitimate model, even in spite of this warning. You can still proceed with a binomial GLM like this. And so if we inspect our model object here, the summary of it, we once again see the dispersion parameter for the binomial family is taken to be 1. That's the assumption, right? It's the baseline assumption of the relationship between our residual deviance and degrees of freedom. It's assumption about the mean variance relationship. But in actuality, it's possible that we've got overdispersion. And the way that I test for that is, once again, just change it from binomial to quasi-binomial and run the model again. If our dispersion parameter comes back to be close to 1, kind of between 0.9 and 1.1, we keep it binomial and we move on as it is. We can use the likelihood ratio tests that I taught you before. Everything proceeds as normal. But if this dispersion parameter comes back as outside that range, then we just need to keep it as a quasi-binomial distribution. And so if we look at the summary output, our dispersion parameter for this quasi-binomial model is 0.276. So that's really small. That's definitely lower than 0.9. As I said before, under dispersion, right, because it's less than the range that we want, it's underdispersed. Underdispersion is less of a problem than overdispersion. It's worse to kind of have a false positive than it is a false negative in many cases. This is a more conservative type of test than it could be if we were to leave it at just a binomial distribution. But if we want to really make sure that we're doing things accurately and as best as we can switch to quasi-binomial. This won't change the predictions that we make, right? Switching from binomial to quasi-binomial or from Poisson to quasi-Poisson doesn't really change the shape of the model. Its ability to predict is still going to be the same. It changes your p-values, because that's really what the kind of unfortunate implication of all of this is. And so in this case, because our dispersion parameter is so small, I'm going to keep this model as quasi-binomial, right? This is now a quasi-binomial GLM. If that dispersion parameter actually looked good, I would go back and just delete the quasi, change this back to a binomial distribution, run that code, and go from there. But because it doesn't look that good, we're going to keep it quasi-binomial. Now, just as we did before, the LR test function won't work for this. Now that we've switched to quasi-binomial from binomial, LR test function is out. It only works for non-quasi distributions. We need the ANOVA function. And so if we feed the ANOVA function our new quasi-binomial model, and we specify test equals f and run that, here's our model p-value, right? We'd report f equals 21.07, degrees of freedom are equal to 1, and our p-value is 0.0017. Again, significant p-value. This is correcting that p-value. If we had kept this as a binomial model, that p-value would not have been accurate. Just as before, if we had kept our first Poisson model as Poisson and not quasi-Poisson because it was over-dispersed, our p-value wouldn't have been accurate. So this is just kind of the final thing you need to do when you're building a GLM. To make sure that your p-values are going to be accurate, to making sure that your model is kind of legit and as strong as it can be. You don't want to be making type 1 or type 2 errors, finding false positives or false negatives in kind of common language. And so this is kind of the consideration that you want to make. Because these Poisson and binomial distributions have a very specific relationship between the mean and variance because they just have one parameter, it's very easy for these types of GLMs to have screwed up p-values. And what you want to do is just play around with it. Make your GLM, but then switch from Poisson to quasi-Poisson, or switch from binomial to quasi-binomial. See if that dispersion parameter in the summary output stays good. If it's between 0.9 and 1.1 approximately, you're good to go. If it's outside that range and you're worried about the impact on your p-values, switch over to a quasi-family distribution and then simply use the ANOVA function with an f-test instead of the LR test function in order to calculate your p-value for the model, your likelihood ratio test. And with that done, you'll then have a perfectly legitimate and much stronger GLM than you would if you didn't account for overdispersion.